Hello. Today we discuss the density of states in three dimension and the phonon heat capacity. Before going to the density of states in three dimension, let us see the number of modes in one dimension using periodic boundary conditions. So in the last class we have discussed the number of modes using the fixed boundary condition. Today we are discussing the same thing using the periodic boundary condition. So let us consider the medium as unbounded. So there is no end atoms which are fixed. So we are not considering the medium to be. We can consider an infinite large crystal in one dimension, that is with a periodicity L. Okay. So the crystal repeats, or the displacement of the particle U of SA is equal to the displacement of the particle after a distance L, okay, after a length L. So this is in one dimension only. In one dimension, we are considering a crystal, unbounded crystal in one dimension. So the solution of the displacement of the particle is USA, where S is an integer, the count of the particle. So this is also like the particles are separated by a distance A, or this is the lattice parameter A, and so there is a length L. So the displacement of the particle U of SA is equal to U of SA plus L. So displacement of this particle and this particle will be identical. Since the particles are unbounded, there is no particle which are fixed. The travelling wave solution, that is U equal to U0 exponential I S K, okay, into exponential minus I omega t. So this can be written as exponential I S K A minus omega k t. Okay. So from this periodic boundary condition, you can write that. So this U is proportional to exponential I S K. U is equal to U of SA is equal to U of SA plus L. So this is the periodic boundary condition. So therefore, exponential I S K A is equal to exponential I S A. Instead of SA, we can replace SA plus L. So I S K A plus SKA plus L into K. Okay, so this is the U of SA is equal to U of SA plus L. So this can be written in this form. Okay, therefore you can write this is exponential I SKA into exponential I L K. Therefore we can write, therefore exponential I L K is equal to 1. Okay. Therefore Lk is equal to e raised to I theta is equal to 1 means e raised to I theta is cos theta plus I sin theta. Okay. So this is 1 means what? Cos theta is 1, that is theta is equal to 2n pi. So 2n pi. Therefore K is equal to, what is L? L is if there are n number of particles, in within this length, that means the periodicity, the length L, then we can write the total length L is equal to, therefore L is equal to n into A. So we can write what is L? 2n pi divided by Na. Or we can write, so this is Lk is equal to plus or minus, you can write plus or minus 2n pi. Okay. So Lk is equal to plus or minus 2n pi, that is, means k is equal to plus or minus 2n pi divided by Na. N is equal to 0, 1, 2, 3, etc. Okay. So how many values of k is allowed, or what values of k is actually allowed for this vibration? So first value, let us take k equal to 0 is allowed. Then here k equal to 0 is allowed because even if this k equal to 0, this displacement is not 0 because exponential I 0 is 1. Okay, so it will be exponential minus I, u equal to u0 exponential minus I omega t. So the k equal to 0 is allowed, which was not allowed in the case of the fixed boundary condition, but here it is allowed. And k equal to 0, then next is plus or minus, if n is equal to 1, 2 pi by Na. 2 pi by Na means 2 pi by L, okay, or we can write 2 pi by L. Then plus or minus 4 pi by L, plus or minus 6 pi by L. Okay. Then finally the maximum value, you know, the boundary of the first Boolean zone is pi by A. Pi by A means what? This is the last value of this will be n pi by n A. So I multiply with n on numerator and denominator, then n pi by n A. What is this? N pi by L. So the final value is n pi by L. Okay. So we can draw this in k space. So the total allowed modes are with the k equal to 0, then 2 pi by L, then the final value will be n pi by L. Okay, so that means n pi by L means pi by A, so the boundary of the first Boolean zone, and towards this side minus 2 pi by L minus 4 pi by L minus 6 pi by L, etc., and the boundaries minus n pi by L. So here we include either minus n pi by L or plus n pi by L within this range. Okay, from between the between minus pi by A to plus pi by A. Therefore, the total number of modes, if you count all these things, total number of modes will be all these things. If you count, the total number of modes will be n between minus pi by A and plus pi by A. Okay. Which is exactly equal to the number of particles which are free to move, which is the same as in the case of the fixed boundary condition. Okay. So therefore, we can write there are one mode in each interval 2 pi by L, in the interval delta k equal to 2 pi by L. Okay. So we have seen how to calculate the density of states in the last class. So same is applicable here also. So the density of states in one dimension is equal to L by pi divided by V. Now let us apply the boundary condition, the periodic boundary condition in the case of a three-dimensional crystal. Okay. So let us consider there are n number of primitive cells in each dimension. That means x-axis, y-axis and z-axis. So the total number of primitive cells is n cube. So n cube number of primitive cells are there. So we are considering a cube of length L. Okay. In each direction there are n number of primitive cells are there. Therefore, we can write displacement u of SA is equal to u of SA plus L in each dimension. Therefore, we can write the general expression of the displacement will be exponential I. Here k dot r it will be because it is 3 dimension. Therefore, we can write kx x plus ky into y plus kz into z, where kx, ky, kz are the component of the wave vector in each axis, x-axis, y-axis and z-axis respectively, minus I omega k t. Okay. So this is the form, the displacement is of the form like this. Now, if we apply the boundary condition, then exponential I kx x plus ky y plus kzz is equal to exponential I k x into x plus L. Okay, so this is u of x is equal to u of x plus L. Similarly, u of y is equal to u of y plus L. So this is exponential I kx x plus L plus ky y plus L plus kz z plus L. So from this we can write the allowed value of kx, ky, kz are 0 plus or minus 2 pi by L plus or minus 4 pi by L plus or minus 6 pi by L, and the last value will be n pi by L. So here also minus n pi L is excluded because we are not counting the first and last element. We are counting either of these two. Okay. If we are counting minus n pi by L, we cannot count n pi by L. Okay, like that. Therefore, we can write one allowed mode or one allowed value of k is present in volume 2 pi by L. Within this range 2 pi by L there is one particle. Okay, similarly in y axis and z axis, so volume 2 pi by L whole cube of k space. So we can draw a two-dimensional k space here. This is in 3 dimension. We plot two-dimensional k space. So in two dimension, within the range of within this area, there is 2 pi by L. So this is 2 pi by L, and this also 2 pi by L. Within the area of 2 pi by L whole square, we have only one allowed value of k. Similarly, in 3 dimension, within the volume of 2 pi by L whole cube, we have only one allowed value. Therefore, the total number of allowed modes per unit range of volume. Okay. Total number of one divided by 2 pi by L whole cube, which is equal to L cube by 2 pi whole cube, which is equal to V divided by 8 pi cube. So here V is the volume of the specimen considered. Okay, for each polarization and each branch. Okay, so we can divide this thing into acoustic and optical branches. So for each branch and for each polarization, so this is the total number of modes per unit volume. Therefore, the total number of modes within a volume of sphere of radius k is given by k is equal to total number n is equal to, so the number of modes per unit volume is V by 8 pi cube into volume of the sphere of radius k in k space. 4 by 3 pi k cube. Here the radius of the k space volume or the sphere is, the radius is k, therefore 4 by 3 pi k cube into number of modes per unit volume is v by 8 pi cube. So the total number of modes is equal to this thing. Okay. Therefore we can obtain the density of states d of omega, which is equal to the rate of change of number of modes with respect to frequency dn by d omega. Okay. But here we have in terms of k, so we can change it into in terms of frequency, that is dn by dk into dk divided by d omega. Okay. So this is density of states is therefore v by 8 pi cube 4 by 3 pi into differential of this thing is 3 k square into dk by d omega is 1 divided by d omega divided by dk. Okay. Now in the Debye approximation, the velocity of the sound is, or the velocity of the vibration is constant for each polarization. Okay. Therefore we can write omega is equal to, the frequency is equal to v times k. Okay. So this is the dispersion relation in this case, or we can write d omega by dk is equal to v. So here d omega by dk is the velocity of the sound wave, and the dispersion relation is given by omega is equal to v into k. Okay. The velocity of each polarization, the velocity of sound of each polarization is constant. Therefore we can write the density of states from the above expression as is equal to v by 2 pi square, this k square is equal to omega square by v square, and d omega by dk is equal to v. Therefore this is equal to v omega square by 2 pi square v cube. So this is the density of states. Now if there are n primitive cells in the specimen, then the total number of acoustic modes is n. So n is the total number of acoustic modes. Now we are considering n number of primitive. Now we are considering n number of primitive cells, and the total number of acoustic modes is n. Okay. Therefore, what is n? The total number of modes is, we know L is n is equal to number of modes per unit volume of K space, that is L by 2 pi whole cube into 4 by 3 pi K cube, where K is the radius of the K space, that means radius of sphere of K. In terms of angular frequency, you can write what is L cube. L cube is the volume of the specimen divided by 8 pi cube 4 pi. K cube is omega cube divided by v cube, where k is equal to omega by v. V is the velocity of sound wave or vibrations. Okay. Divided by 4 by 3 pi k cube. Okay. So on simplification we get v divided by 4 get cancelled, pi cube, so therefore pi v by 6 pi square v cube omega cube. So this is equal to n, total number of acoustic modes. So that is fixed because the total number of primitive cell is n. Correspondingly, there is a cutoff frequency because n is fixed. So omega d is equal to 6 pi square v cube n by v whole raised to 1 by 3. Okay. So this is the cutoff frequency. Okay. And cutoff wave vector kd is equal to omega d by v, which is equal to 6 pi square n by v whole raised to 1 by 3. So this is the we have calculated the number of modes in 1 dimension and 3 dimensions, and we also calculated the density of states. Now we have to obtain the total thermal energy of the crystal and heat capacity, so that we will discuss in the next lecture. Okay.